understand this? And we understand this by looking at the expression of the my double prime, because that is expression of internal moment. You notice that this whole thing actually depends on the signs of this, it depends on the signs of y double prime. You can write down the expression in terms of the y double prime. We're going to write it like this. So we know that y double prime x is written as k squared ma cosine kl plus mb over p sine l cosine kx plus k ma over p times sine kx. And not necessary to be 0 is this. So what it means is what? What it means is that we can do the same thing by taking the MB out of it. So this whole thing can also be written as expression of.
Professor, I think cosine should be sine, and sine would be cosine in the y double prime expression.
Is that right? Yes, you're right. Sine, cosine, cosine, sine. Thank you. So the first one should be sine because it's second order derivative, right?
Also,
right?
K ma over p, I think it should be k squared ma over p.
The k, this should be also another square, right? Thank you. So this will be times cosine. Okay, like this. But similar to the example of y of x, you know the y double prime of x can also be written as the whole thing in terms of mb times all of these, right? So what does that mean? That means if you look back to the expression here, the way we're going to determine the maximum moment, it depends on how the entire function can be written as a function of mb. Of course, you can do the same thing with ma. But if you choose mb, it means we will look at total moment like this. Suppose we have only an mb, which is here, like this. And then, of course, ma is still ma. We assume that ma is not 0, so you still have an ma something like this. So this will be your ma. Now, this is the positive direction, which is important here. This is the positive direction of MB that we assume, which means that if MB is positive and MA is positive, and the structure will end up like what? The moment will actually be the one we just developed here, right? This will be the actual M moment, which means it's gonna look like something like this. Something like this. If the moment distribution is like this, what about the actual deflection? The actual deflection will also be like this. So that indicates that if whatever the coefficient, this coefficient here, is greater than 0, that means MB is going to be positive. And that means this whole thing will be a double curvature. Will be a beam column in double curvature deformation, correct? Because MB is positive. If that sign is positive. What happens if the sign becomes negative? If the sign becomes negative, your MA is still here because that's a positive definition of MA. So MA is still here. MB this time, it will change from positive to negative. So how do you express a negative MB? How do you express that? You just flip it. So here, downward here, there used to be the positive MB. To make it negative, that means you will have to change the sign. When you change the sign, it will be flipped to where? To the top. That means this will be where the new MB is going to be. And if you use a different color, you can see that it's actually going to be something like this. So this is the case when we have negative minus MB. Would you agree? Right? So here, this is positive MB and this is negative MB. MB, because now it becomes negative, to its original definition. In that case, the original column or the moment distribution will become something like this. With the second order effects, the total moment distribution will be something like this. In this case, obviously, you can see that it is not a double curvature beam column, right? Now will actually become a single curvature column. In other words, the expression that we have from before we can actually tell that internal moment is negative EI times Y double prime, which also equals to negative sine of MB times an expression. We can represent it this way and by bringing the EI into this whole thing. And then all you need to do is just to determine what is the sign of this expression here. So what we learn from this analysis is what? Is the coefficient associated to MB. You can also replace this MB with MA, and of course we'll give you the same result. But if we choose MB, then we use MB as the reference point, and to compare the sign of this one to determine whether it's a single curvature or it's a double curvature bending. But in the single curvature bending, the same way that the maximum moment would also be pushed from the end to somewhere between two supports, which in this case, this is where the maximum moment is. So from here, of course, the original one, we changed it. If I want to keep it like this, in this case, this is the maximum moment. Presumably, I know the quantitatively probably does not look exactly the same. And then if we can express the expression this way, then we can just look at this sign, the sign of this coefficient, to determine that whether it's greater than 0 or less than 0. And then we have different approaches. If it is single curvature, by assuming that the whole coefficient is less than 0, and at the maximum moment, we know that shear must be 0, correct? Now, if shear is 0, what happens to the expression of the curvature? That means it's the third order derivative of y. That means y, the third order derivative of y with respect to x must be 0. And then we call the expression of third order derivative of x. And this one here is k to the cube ma times cosine kl plus mb p over sine kl times cosine kx plus k cubed ma over p. We still have L here. No L here, right? This will be sine x. This has to be 0. And what we're going to do is to move cosine and sine, separate these two, move to the both sides, and divide everything by cosine. And if we do that, you will get expression of tangent. That will give us this. Tangent kx would be this, which is ma cosine kl plus mb negative divided by ma sine kl, and the p will be cancelled out. So when the third order derivative of y with respect to x becomes 0, and that means this must be true. And if this is true, that means at the location when this condition holds, that is the location where the maximum moment occurs. And that means this x, we're going to let x equals x bar. That means this is where the maximum moment occurs, when m equals mx bar. So this is the condition we set. That means the definition of this. And that means we're going to put a bar on top of this x. By evaluating this, the location of this x, we can determine the location of the maximum moment. And that's how we're going to determine the maximum moment. Because we already have the expression of y double prime. So as long as you know the location of x, you can just substitute the value of x to find the maximum moment. So that's approach to find maximum moment. And let's continue finding this value. How do you determine the value of kx? First of all, take arctangent. So kx bar equals to arctangent of this whole thing. Negative ma cosine kl plus mb divided by ma sine kl, like this. And how do we find x bar? X bar is just 1 over k times tangent, arctangent of whole thing. Like this. So this will tell you how do we find the maximum moment. Once you find this one, as long as you know the value of ma and b, you plug it in, then we can know x bar, right? So once you found x bar, how do you do it? You plug in x bar into the expression of y double prime, the second order derivative. Then you can find the maximum moment. Therefore, here you can say that maximum moment will equal to negative ei times y double prime at x bar. You already have expression of y double prime, so that's how you can find the value of maximum moment this way. So this approach is slightly different from the one we did before, because before we assume that we know the location of maximum moment. If the loading is symmetric, usually occurs at the midspan. But in this case, we don't know that because we don't know the value of ma and b. That's why we had to do it this way. Okay. Now,
is that the case for both single and double curvature?
Yes, the approach is the same, but the expression for x bar is slightly different. In this case, we assume that MB is positive, and that makes this whole thing, this sign is positive, right?